Welcome back to the Chem OG. Today we're going to take a look at a fun little topic with relation to gases, and we're going to check out something called Graham's law. Now, Graham's law is called Graham's law of effusion, and effusion is just a fancy word for escape, right? If someone is effusive, that means that their emotions escape readily. And so Graham's law of effusion refers to how well molecules can escape. And if we want to analyze how well it is that molecules can escape, what we need to take a look at are their speeds. The faster molecules can move, the more readily they can escape. So if a molecule moves 10 times faster than another molecule, it can escape 10 times more readily simply because it covers, in that same time span, it covers 10 times as much distance. That's what it means to be 10 times faster. And so today what we're going to take a look at are proportions. We're going to compare something to something else. In particular, what we're going to take a look at are comparisons of speeds, how fast molecules can move. And so one important equation that comes up is that the average kinetic energy, when we take a look at gas molecules, the average kinetic energy of gas molecules is related to their temperature, their absolute temperature in the Kelvin scale. And so if a certain molecule has a higher temperature, it also means that its kinetic energy is that much higher. If we double the temperature, we're doubling the average kinetic energy of our molecules. And so if I have a collection of molecules, 2 gases, 3 gases, whatever. If I have a collection of molecules that are in the same container at the same temperature, if their temperature is the same and R is the gas constant, it also means that the average kinetic energies of all the molecules that are in that same container are going to be the exact same. And we have a pretty handy dandy equation for being able to determine the kinetic energy of an object or a physical object. And so we're going to use that and apply that equation to gases. So let's take a look at an example. If I'm trying to compare 2 gases, methane and helium, what I want to know is which gas escapes a container more readily. And if I can find out a little bit of information about which one, does what and a comparison of their speeds, that would be nice. What I'm trying to figure out is a comparison of their speeds. Well, if both molecules are in the same container, it means that their kinetic energies are equivalent to each other. And so the equation for kinetic energy is mv squared over 2, or 1/2 mv squared. And so that means for both methane and for helium, 1/2 mv squared applies to both, and those quantities are going to be equal to each other. So we can drop 1/2 from either side of the equation, and we end up with this relationship that the mass of methane times its velocity squared is equal to the mass of helium times the velocity of helium squared. And so we're going to start with that same relationship, but remember, if I want to figure out which gas escapes more readily, what I really need to find out is a ratio of velocities. And so what I'm going to do is I'm going to divide both sides by the velocity of helium squared. I'm going to put this over here, and I'm also going to divide both sides by the mass of methane, and I'm going to put that on the other side. And I end up with this relationship right here, that the velocity of methane squared divided by the velocity of helium squared is going to be equal to the ratio of the masses. Now notice something very, very important is that whatever term in velocity up here is, in this case it's methane over helium, the masses on the other side are reversed. So here I have the velocity of methane up top. Here I have the mass of helium up top instead. And so we know what that ratio of molecular weights is because I know that the mass of helium is about 4, and the mass of methane is about 16. I have 1 carbon that's got a molecular weight of 12, and the 4 hydrogens are going to add 4 more. So my ratio of mass of helium to the mass of methane is 4 to 16, or 1 to 4. Okay. And so that is the ratio of the velocities squared as well. So if I want to figure out the ratio of the velocities by themselves, I would need to take the square root of 1/4. And when I do that, I will find out that my ratio of my velocity of methane to the velocity of helium is 1 to 2. So what that relationship tells me then is the following. It tells me that the velocity of helium is twice that of the velocity of methane. And because we now have a ratio of the two velocities relative to each other, I can say because helium is twice as fast, it covers twice the distance in the same amount of time. So what we have really here is a powerful relationship, and that is that we can find out the relative velocities of two different molecules by taking a look at the ratios of their molecular weights. And in general, that relationship looks like this, that the velocity of one molecule compared to the velocity of the other is equal to the square root of the proportions of their molecular weights. But notice here that if V1 is on top on one side of the equation, then it's M2 that's on top on the opposite side of the equation. And that's because the mass and the velocity have an inverse relationship with each other whenever you have two different molecules that have the same kinetic energy. And that general relationship is known as Graham's law of effusion. And put in very, very simple terms, smaller things move more quickly and larger things move a little bit more slowly. Thank you for watching today's episode of the Chem OG. Please be sure to help support this channel by liking and subscribing.